Hello everybody. Welcome to the serious security seminar. This week we have a faculty member from Purdue, Abul Her Safarano, and he works on statistical machine learning and its application to natural languages and their understanding as well as reasoning. And he's focusing quite a lot on LLM these days. And without further ado, Abul Her, please go ahead.
Thanks so much, Aniket. Yeah. So today I kind of want to talk about uh, kind of more recent work that I've done over the past few years, as well as more recent papers this year, kind of exploring the abilities of language models to be able to learn how to reason, and whether, current models can reason, and if not, then can future models potentially reason or learn to reason. Um, and Basically, I mean, if you look at the headlines these days, last year you saw, a lot of hype around language models, basically by the pace of their advancement of the capabilities. It seemed to be very impressive to a lot of people. Um, People were, hyping it up to the point where, benchmarks were showing they were competing better than humans on like the medical school entrance examinations and law school entrance examinations, right? The LSAT and the MCAT. Um, so, uh, I mean, does that mean that these language models are now capable of practicing medicine and law? Um, and the answer is no. You haven't seen like doctors and lawyers being, wholesale replaced by language models, right? And you see like more careful studies of these abilities of these models, kind of showing that they do have some shortcomings. Even this year with GPT-5, the hype seems to have become a little bit more tempered, right? Even like Sam Altman, the OpenAI CEO, is admitting that there could be a bubble, perhaps. Maybe there's a bit too much kind of expectations, right, for the capabilities of these models. So that kind of brings us to our main two questions. Can current LLMs reason, and can future LLMs reason? And we'll start with the first one. So Um, chain of thought prompting essentially was the kind of the development that has led to a lot of people to think that or suspect that, oh, maybe LMs might have some reasoning capabilities because they suddenly were able to do a lot better on a bunch of reasoning intensive benchmarks like answering math word problems, right, or logic puzzles. Um, so in contrast with direct prompting, where you just have, let me turn on my data point here. So you just have the question here, and then the model just gives you the answer directly without anything in between, right? In chain of thought prompting, you have the question, and then you ask the model to provide some reasoning, some sort of verbalized reasoning to explain its process for coming to the conclusion or the answer, right? And this kind of prompting kind of really does improve the model's ability to, maybe not ability, but its performance, its measured performance on a lot of reasoning intensive benchmarks. But I mean, do those results on those benchmarks kind of prove that these language models reason? Uh, and we have some doubts because there are some confounding factors, right? One is data contamination, and this is a big problem with evaluating language models and generative AI these days. Is that oftentimes the training sets for these large models contain effectively anything on the internet, and that includes a lot of the very same benchmarks that are used to evaluate them, right? And so instead of testing for a model's reasoning ability, we might be kind of mistakenly testing its retrieval ability if it's something that it had memorized from training, right? So a benchmark may ask the model to deduce something that already knows from pre-training. Another potential confounder is, poor out of distribution generalization. The model may rely on shortcuts such as heuristics or spurious correlations that may have worked well to answer the questions in its training set, but they don't work well when asking questions outside of its training set, right? The other thing is that a lot of these, existing benchmarks that look at reasoning, they really only inspect the label accuracy. So they look at the model's final answer and kind of ignore everything that happens before that, right? But what we're kind of interested in is like what happens before that. Like, is the model actually correct in its reasoning? How does it actually, search from, the premises and find the correct path to the goal, the conclusion? And so we're more interested in what we call proof accuracy, which is how correct is this kind of step-by-step process. So we want to more precisely and systematically measure the reasonability of language models. And so to do so, we will formally analyze their predicted chain of thought, right? And we do so by first, we parse each sentence of the chain of thought into a logical form, right? So here, Alex is a cat, all cats are mammals, Alex is a mammal. It gets converted into these three logical forms. This is just in a kind of simplified first order logic, right? Uh, cat of Alex for all x. If x is a cat, then x is a mammal, and Alex is a mammal here. And then for each logical form, we then check to see if it's deducible from previous logical forms via some rule of inference or deduction, right? So here we can see that, given Alex is a cat and all cats are mammals, we can conclude that Alex is a mammal. But if we want to do this kind of analysis, we need to have some sort of question answering data set where the sentences are simple enough to be parsed semantically, right? Ideally, this data set should allow us to control for all the confounding variables that I mentioned in the last slide. And so to do this, we introduce a new data set, which we called Pronto QA. Um, and this is detailed more in papers from last year and the year before. Um, but basically, we want to make sure that we can control for data contamination to ensure that the examples we create are not in the training set of these models. And to do this, we make it a synthetic data set, which means we generate the examples ourselves. Um, Right. And also the synthetic nature gives us a lot of control. We can tweak variables, in any way we want to run very, very, well-controlled experiments. Um, so to generate each question answering example in Pronto QA, we first generate a graph looking like something like this. So you can see that each of these vertices represent some sort of concept, right, or entity, and then these edges represent some relation. In this case, it's like a subtype relation, right? Um, And then what we do is then we convert each edge into a sentence that'll form the body of the question. So in this case, we're apparently looking, kind of traversing the edges in top-down order, right? This edge from animal to multicellular is being translated into each animal is multicellular. This edge here, vertebrate to animal, goes to vertebrates are animals, right? And so on and so forth. Next, we actually just pick some node in the graph and then perform a random walk of length k, right? Where k we can control as a parameter, right? Each hop in this random walk corresponds to like a reasoning step, right? So you can see, let's say we pick this kind of walk over here from cat to warm-blooded. For each step in the walk, we then generate a chain of thought sentence. So kind of how the model should think about reasoning and solving and answering the question that we're going to generate. So in this case, we say, starting with Alex as a cat, and we know from the fact that every cat is a feline that Alex is a feline, right? And then also, since all felines are carnivores, Alex is a carnivore, and so on and so forth until we get to Alex is warm-blooded. And then we can just take the endpoints of this walk and generate the query, right? True or false, Alex is warm-blooded, given that Alex is a cat. And so we could just concatenate all of these pieces together, and we end up forming a full example like the one detailed here. So to test how much the model relies on knowledge acquired from pre-training rather than actually performing reasoning to solve the problem, we generate three different kinds of ontologies or graphs. Right. The first is what we call a true ontology or a true graph, where basically all of the facts in that graph are consistent with the real world. So they look like things like all cats are mammals, right? Another kind of ontology we generate are false ontologies, and these are graphs that contain things that are inconsistent with the real world. So all mammals are cats would be an example. And then we also generate fictional ontologies, and this is to make sure that the example that we generate is completely unseen and irrelevant to what the model has seen before, right, in its pre-training. Um, and we just replace all of these kinds of concept names with fictional names, like all wumpuses are vumpuses, right, just to uh, make sure that the model isn't getting tricked up by any previous knowledge about cats or mammals. We also add distractor sentences to prevent cheating, like heuristics. Um, and because we also formally analyze the model chain of thought, we're kind of checking the model's work, right? It is more difficult for the model to kind of cheat. Um, so the model kind of has to, do the step-by-step reasoning correctly in order to get kind of full points according to our metrics. We use few-shot prompting to kind of encourage the model to generate easily parsable chain of thought sentences, right? If you just ask the model the questions without any other context, the model's response might be very open-ended, but that would be much more difficult to, apply a semantic parser and convert those sentences to logical form. Right? And so few-shot prompting kind of helps us to um, kind of guide the model to output its chain of thought sentences in specific kinds of forms. And so here are some results from that analysis where we have different sizes of this is GPT-3 models, um, and then the proof accuracy as a function of the model size, right? And you see that larger models just tend to be better at this kind of task than the smaller models. And in fact, larger models with better post-training, such as instruction tuning, are better than models without that kind of post-training. And so henceforth, let's just focus on this largest model. We also compared what happens if you change the type of the ontology or the type of the graph, like whether we're using fictional facts, false facts, or true facts. And as you can see, there's this pretty big gap between the true ontology and the fictional false ontologies, right? Which suggests that these models are in fact kind of leveraging prior knowledge about these, concepts like cats and mammals and things like that to kind of, uh, get an advantage in answering the questions correctly. Um, but if you instead replace the concepts with fictional ones, right, or just make the facts false, you see a much lower performance. And also we considered different lengths of random walks, right? So 1 hop, 3 hop, 5 hop. And we saw at least back in GPT-3, 5 hops was still very challenging for these models. Nowadays, they're not quite challenging, but I'll get to that later in this talk. One kind of very interesting question that we wanted to ask though was um, we know from these experiments roughly how well models can, produce an accurate chain of thought holistically, right? But then what about each step? Like how are the models actually predicting or making individual steps within the chain of thought, right, to get to the answer? Um, and so to do this, we categorize the mistakes the models will make. For each step in the chain of thought, we will check to see if it's correct or incorrect. And if it's incorrect, we will categorize it into one of a few kind of classes of errors, right? The first class here is what we call invalid steps. And these are kind of proof steps that just don't follow logically. They're not valid. So like 4 is an integer, all primes are integers. 4 is a prime is not a valid conclusion you can draw from these two premises, right? The other kind of mistake or mistaken step or an error in the step would be a misleading step. So let's say our goal is to prove that Alex is warm-blooded, right? And we know that Alex is a mammal. Um, Ideally, from this point, I would say, since all mammals are warm-blooded, therefore Alex is warm-blooded, and I finish the proof. But sometimes the model will just pick some other fact entirely, right? All mammals are vertebrates, therefore Alex is a vertebrate, right? And this is considered a mistake because even though it's valid, it's not really helpful for solving the question, right, that was posed. And so what we can do is we can kind of break down this bar chart into like this little sub or nested bar chart, where this dark red bar here indicates the proportion of the incorrect proofs that contain a misleading step. And the dark red bar over here on the right side is the proportion of incorrect proofs that contains an invalid step. And similarly for this dark blue bar here, that's a proportion of correct proofs that contains a misleading step. And this is the proportion of correct proofs that contains an invalid step. And there are some other types of errors that we looked at as well, but these two are kind of the most important ones that we recognize. Um, and we can observe from this that most incorrect proofs contain a misleading step and an invalid step. So then one thing that we ask is uh, which of these kinds of errors actually causes the model to make the mistake, to get the entire question wrong. Um, and so to kind of test this, we now plotted here what is the type of the first mistake the model makes in its reasoning, right? So this green bar, for different model sizes, you see this green bar is the proportion of incorrect proofs where I should show these labels, where the first mistake is a misleading step. And the red bar is the proportion of incorrect proofs where the first mistake is an invalid step, right? And so if you look at kind of like these smaller models, most of their first mistakes are invalid steps, right? But then as you get to larger and larger model sizes, you see that instead, misleading steps becomes more commonly the first error, right? And then invalid steps become less frequent in general becomes less frequent. And so from this, we can kind of, draw a conclusion that while LLMs are pretty good, at least large LLMs with good training, are pretty good at making valid deduction steps, like individual steps that are correct, on its own, they struggle with kind of a more general, like a global picture, where they have to kind of know what direction to make a step, the path to get from the premise to the conclusion, right? And so this kind of skill is called proof planning or proof search, right? And this seems to be where these models seem to struggle. And this kind of suggests some more fundamental limitation in the model's ability to perform search more generally. And you see that in a bunch of other benchmarks as well. Okay, so what about reasoning models? Um, More recently, LLMs that are post-trained with reinforcement learning have significantly improved performance on reasoning tasks, right? And including Pronto QA, like these reasoning models will solve Pronto QA questions, very easily, very accurately. Um, and just to kind of give you a demonstration for like how much of an improvement there is in this kind of development, um, these first three columns are language models that were not post-trained with RL. So they're just kind of vanilla LLMs. Whereas these three columns on the right side are large reasoning models, right? They were post-trained with RL. And basically what uh, what these models are trained to do is that they're actually um, uh, trained to create a very long chain of thought, kind of what they call a thinking token or reasoning tokens, right? And this can be very, very long, like tens of thousands of tokens long. Um, but the idea is that if the model spends more time producing these reasoning tokens, what's called test time compute, right, then it's more likely to get the final answer correct. And you do see that actually this big difference in some of these benchmarks. So for example, Alpaca Eval 2.0 gets a 52% for the cloud models, but jumps up to 87.6% for DeepSeek R1, right? These math competition data sets, the AME 2024 benchmark, right? These vanilla LLMs don't do too well, but then once you use RL, these large reasoning models, do significantly better on these tasks. Same thing for code generation as well as other kinds of reasoning tasks. So does that mean that RL kind of has solved this shortcoming in the language model's ability to search? Um, There was earlier this year, a recent paper by Apple, by Shoje et al. In I forget exactly which month it came out, but they tried a different set of tasks, such as this is kind of a Tower of Hanoi task where you're given an initial state where you have disks stacked in a particular order on one peg, and you have to kind of move the disks around until you can get to a target state where they have to be stacked in an order in a different peg, right? Um, and they show that if you change the number of disks, right, by adding more disks, you make the problem more and more difficult to solve, right? The the vanilla LLMs like this Cloud 3.7 Sonnet, um, they kind of do well up to a certain point, and then they suddenly start doing poorly, right? But if you use large reasoning models, like this model has like a thinking mode, which allows you to kind of use it like a large reasoning model, right? Then it performs well for more complex problems, right? But there's also some limit at some point, in this case, 8 disks, where even those models seem to, begin to perform just as bad as the vanilla LLMs. Um, and so this has kind of led to some people to think, oh, maybe, RL has helped these models to reason on slightly more complex examples, but not on like unboundedly more complex examples, right? Um, but their methodology has a few flaws, right? So in some tasks, including the Tower of Hanoi, in the tasks that they studied, they required exponential number of steps to solve, right? And so it's not very, very fair to ask a language model to solve those tasks when even like a human would struggle with an 8 disk Tower of Hanoi task, right? And also one possible confounding factor is the number of generated tokens may have exceeded the context limit, right? So these language models have some context limit where they can see a maximum number of tokens and process them at any given point in time. Um, but um, these LRMs, as you recall, they generate very long chains of thought. So it's possible that it has generated so many tokens that they hit this context limit, and that's what's causing this drop in performance, right? As opposed to any, more fundamental limitation in the model's ability. So to address these potential confounders, we extended our Pronto QA dataset to generate very large graphs, like much larger than the ones that I showed earlier, right? And we measure complexity using this metric that we call look ahead, right? So given a graph, start vertex, a goal vertex, the look ahead is the number of breadth first search steps or BFS steps that you need to find the goal from the start vertex, right? So you can imagine that if you need more steps to find the goal, then you have a more complex graph, and your graph will naturally also be larger as well. We also measure complexity with respect to the number of branches, and this is kind of like the number of paths in the fork from the start vertex. So it's more precisely just the number of child vertices of the start vertex. We test these LRMs, these large reasoning models, on 2 tasks. The first is given a graph with a start and a goal node, predict a path between them, right? So here's an example graph, and this is kind of how we would prompt the model, right? And so the model just has to output like a sequence of vertices that goes from the start vertex to the goal vertex. The second task that we test is given a natural language reasoning problem, like something like this. It's kind of like a logic problem, but expressed in natural language. Um, Given a starting premise, like here, given that Fei is INESAM, um, and a goal conclusion, we want to prove Fei is DETMI, we want the model to predict the next step in the proof. So this task is a little bit easier because you don't have to provide like the full proof. itself. We just want to get the next step, potentially. Right? And you can see how this kind of problem can be mapped to this equivalent underlying graph structure. Each of these clauses kind of can be correspond to a vertex, right? And then the edge corresponds to sentences of the form if A, then B, which indicates there's an edge from A to B. And yeah, if you want to read more about the details of this, I recommend you read our recent archive paper. One kind of critical difference between our task, this graph search task, or both of these tasks, and other tasks like Tower of Hanoi, is that our tasks can be solved in linear time, right? They're actually pretty straightforward to solve. Um, and only a linear number of thinking tokens are needed, at least with respect to like the graph size, right? And so we call this data set the deep reasoning data set or deep RD data set. So just diving right into the results here, we see, um, so this is when the number of branches is 2, and we increase the look ahead of the examples, and then we measure the accuracy of if the model can produce the correct path from the start to the goal vertex. And this is in the graph search task. So this is when the model is given like the graph in like a symbolic form. And these different colors, lines indicate different models, right? So GPT-4o and DeepSeek V3 are examples of LLMs, right? Whereas R1, O3, and O3 Mini are examples of LRMs. Right? These are reasoning models. And you do see this very similar gap that we saw in the Apple paper, right? Where the LLMs kind of uh, drop in performance even with pretty small look-ahead values, right? The LRMs, however, seem to do reasonably well for look-ahead values up to like maybe 64 or so. Um, but then after that point, they also began to deteriorate in their performance. Um, One thing to note is that O3, this model is very expensive to run experiments with. So we only did, I think, 2 points for each of these. Um, but you can see like O3 isn't performing especially better or worse than any of the other reasoning models on this task. The other thing is that we also measure the accuracy on this kind of the deep proof search task. So this is when we give the model the natural language logic problem. Um, and it only has to predict the next step along the proof, right? Um, and so you see that the accuracies are higher here, but that's because, if you were to randomly guess one of the two uh, children of the start vertex, you would get an accuracy of 50%, right? And so 50% is like kind of the random guessing chance here. For B equals 4, it's 25%, and then 12.5% for 8, and so on. But you see kind of roughly the same pattern as in the symbolic graph search task, where uh, after a certain point, all the models, both LLMs and LRMs, began to struggle on this task. What's interesting is we included this result where we set the number of branches equal to 1. So that means that the graph is actually just one long linear chain, right? Um, the edges, though, they're kind of shuffled in the order when we present them to the model, just so that it's not too easy for the model to just kind of copy the edges in sequence. Um, but essentially, this becomes kind of like a pointer following task, right? Can I, follow the sequence of edges and just, write down the order of vertices that I have visited? Um, and you see that these models actually do pretty well up to like about 500 or so kind of distance. But then after that point, then they begin to struggle. But this may be due to the fact that, when the model is kind of doing some sort of repetitive action, like outputting a token, um, and there's some small chance of error for each action, um, then the overall error will compound and grow exponentially if the number of actions, the sequence length grows, right? The other thing that we wanted to test is whether the context limit was a limiting factor in the model's inability to kind of solve this task accurately. And we saw very similarly to the Apple paper that, for small look-aheads, the context limit, the number of tokens the model generates in its kind of reasoning grows as the complexity of the tasks grow, up to a certain point, like around 64, it seems, the model kind of stops generating more tokens or thinking more to solve the problems, right? And then at that point, it just kind of like levels off and even decreases. Um, O3 is very expensive, generates many, many more tokens, but it's still well below the context limit of these models, which is at least 32,000. So why do LLMs and LRMs fail to generalize, right? So one thing that we hypothesized in this paper was that they may be limited by the underlying transformer architecture itself, right? Which tends to kind of overfit to its training distribution. And this kind of leads to poor out of distribution generalization. And to get a sense of the complexities of graphs, and proofs in the training data, we decided to analyze a bunch of public data sets of graphs, as well as one data set containing proofs called the natural proofs data set. And these are human annotated proofs. And so for each graph and each proof in all these data sets, we computed the look ahead and the number of branches of each example and cultivate them together and visualize them in histograms, right? And these are those histograms. Um, the red lines denote the 50th, 75th, 90th, 99th, and 99.9th percentiles, respectively. Um, the first row, we plot the look ahead, right? Um, and then the second row, we plot the number of branches. Right? And different columns denote different data sets. So you can see the first column is ConceptNet. This column is OGB. The last column is the proofs data set. And we're missing the number of branches histogram here because whenever you're doing proofs, you can easily come across a vertex that has an infinite number of branches. For example, if I have something that says that for all x, f of x is true, then I can deduce either f of a, f of b, f of c for any possible substitution of x. I can deduce f of anything to be true, right? So that vertex, that node, is for all x, f of x has an infinite number of children. Um, and so that's why we kind of didn't plot this number of branches for the proofs because it's not really well defined. Um, but overall, you can still see that you know, it is very, very rare to find examples with more than, say, 10 to the 2, 100 look ahead, right? The vast majority of examples in the training in these data sets have much smaller look ahead, as well as a smaller number of branches. Yeah, and you can see that they tend to follow this power law very clearly in the bottom row. Right. So that would go away to explain why these models are not able to generalize to more complex examples, is that they just really haven't seen that many examples with that level of complexity. In a separate study, actually, we asked LRMs to solve synthetically generated math word problems. And we use a really cool logic programming framework to generate these problems. And if you want to read more about them, um, I invite you to read the paper, which I'll cite here. I think it'll be presented at NeurIPS this year. Um, so for each example in this data set, we compared the length of the LRM's output in terms of the number of reasoning tokens that it produces while trying to find the answer, right? And we compare that to the length of the shortest proof in terms of its tokens, right? And we were able to generate these examples such that we can be sure that we know the length of the shortest proof, right? And then we again plot these lengths in a histogram. Um, so this blue histogram is the histogram of the lengths of the shortest proof, whereas the orange one is a histogram of the lengths of the model's outputs, right? And you can see that in general, these are different models being plotted. Um, that the model is definitely generates a lot more tokens than the shortest proof than it needs to. Um, this QWQ 32 billion model is interesting because it seems like it's closer, but at the same time, there's this kind of long tail of examples where it probably got those examples incorrect, but it just kept spending more and more time searching and generating reasoning tokens to no avail. Okay. Any questions about that first part before I move on to the second? I'm also happy to
So
take questions
generally the
after.
question appears in Q&A and people expect question in the end. So you can continue. I guess probably we'll have the whole Q&A session in the end then.
Okay, yeah, that sounds good. I can do that then. Thank you. Yeah, so now I want to move on to the question of like whether future models, language models, can learn to reason. Um, and we will tackle this from the angle of using scaling laws. And basically, they were first described, or maybe not first described, but they became widely known from this paper, this Kaplan et al. Paper from January 2020, where basically they trained language models on the next word prediction task, the language modeling task, where you just have to predict the next word conditioned on the previous words, right? Um, they measured the loss function as a function of how long the training was taking. So this compute means training compute, right? You can think of it as as you train for longer, you go further and further to you use more and more training compute, right? You go further to the right. Um, and what happens when you train these models is that, their loss function begins to decrease. And then at some point, it reaches this point where like it stops decreasing quickly, right? Um, and kind of like levels off. But if you increase the size of the model, slightly, then it takes a little bit longer for the model to learn, but then it reaches a lower test loss before kind of leveling off, right? And then this seems to continue in a very predictable pattern, right? Where larger and larger models, they need more compute and more data to train, but they're able to reach a lower loss value um, after doing the training. And as you can imagine, this was very exciting for OpenAI. Microsoft was convinced to invest in them heavily. And a few short months later, they released GPT-3 by essentially, pushing this formula, to much, much larger model sizes. So, but these earlier scaling laws were focused at the next word prediction task, right? Um, and so what if we ran the same experiments, but with the search task instead? And that would kind of give us some insight as to whether scaling these transformer models, these language models, into larger and larger sizes, whether that will actually help them learn to search. And so we construct examples like this, where we have some sort of graph, a start vertex, a goal vertex, so very similar to the setting from before. Um, but we want to have the model predict the next vertex along the path to the goal, right? And then what we do is we kind of translate this graph into this sequence of tokens, right? Which we then give to the transformer as input. And we train the transformer model on these kinds of inputs, on many, many inputs of this type, right? And this we describe in our iClear paper from this year. So if you want to read more about that, I suggest you look into that. In our experiments, we will vary both the size of the model in terms of number of parameters, as well as the complexity in terms of number of vertices of the graph. So this is the first experiment where we vary the size of the model, the number of parameters of the model, right? And you can see that for this light green, we have 4 of them because we ran the training with 4 different initial random seed values to get a kind of idea of like the variance um, in the training dynamics. And we see that there is quite a large variance, right? It's very sensitive to the initial random seed, it seems. Um, but at the same time, we see that there is no observable kind of pattern between the model size and the train dynamics, like how quickly it learns, the task, the search task. However, if instead we kind of try to vary the graph size, right, the number of vertices, while keeping the model size fixed, there's this very clear pattern where it's much easier to learn how to search on smaller graphs as opposed to larger graphs, right? The loss function decreases much faster when trained on smaller graphs. And you can visualize this differently where, let's say I want to measure what is the smallest test loss the model has achieved after a certain number of training examples or compute, right? And I plot that as a function of what is the size of the graphs the model is being trained on, right? And as I increase the size of the graphs, then the minimum test loss increases, suggesting that the models have more and more difficulty learning how to search on increasingly larger input graphs. But what if we allow the model to output intermediate steps, like in chain of thought, right? Like what large reasoning models do, for example. So we instead try to teach transformers to perform depth-first search, right? So we give the same kind of input as before, except the last few tokens are essentially like a trace of the depth-first search up to a certain point, right? And the task of the model is to then continue and predict the next step in the DFS, right? So here, let's say the model started at 8, visited 4, and then 1. So the next correct step could be 3 here. And again, if we plot, we fix the model size and we vary the model size, the graph size, the size of the graphs, we see that for both the training loss and the test loss, it's much easier to learn how to do depth-first search on smaller graphs than larger graphs. And instead, if we now fix the graph size and vary the model size, the transformer number of parameters in a transformer, we actually see something counterintuitive, that the smaller models tend to be quicker to learn the task than larger models, right? So this is kind of reverse of what you'd see in the next word prediction task. And this kind of suggests that, that larger LLMs are not better at learning how to search, right? From these scaling law kind of observations. It also becomes increasingly difficult to learn how to search on larger graphs. And that stays true even if we use like depth-first search or chain of thought prompting. And maybe it's this inability to search has kind of led to this plateau of AI capability that people are, talking about, like in the news, that OpenAI and Sam Altman are talking about. But then maybe not. And we asked this because we actually tried some other kind of analysis to determine whether transformers are learning some sort of, generalizable, robust graph search algorithm, within the parameters somehow, right? And so to try to answer this question, we apply what is called a mechanistic interpretability analysis to the models. And we apply this analysis to the models that we trained in the previous experiments, but only the ones that achieved very high accuracy, right? The goal of mechanistic interpretation is to essentially reverse engineer the algorithm that the model has learned to perform the task, right? I'm going to skip the details of this methodology for the sake of time, but if you want to read more about it, I refer you to the iClear paper. So what does the algorithm actually look like? The algorithm that we kind of infer that the model is learning, right? Well, suppose we have this kind of simple graph. It's just a chain from 0 to 9. You have 10 vertices in total, right? The token for the vertex 1 initially stores information about itself, right? It hasn't actually done any processing yet. This is the first layer, right? And so same thing for the token for vertex 2. It only stores information about itself, the vertex 2. What happens in the first layer is that actually this token for 1 attends to the token for this vertex 2. And so it copies the representation that's stored in the vertex for 2 into 1. So now this token for 1 contains information about both vertices 1 and 2. Layer 2 does the same thing essentially. So by the beginning of layer 3, now the token for 1 stores information about vertices 1 through 3. And then this process essentially seems to repeat, right? And it's fascinating because this is actually a very kind of well-known parallel search algorithm where at every vertex, we're kind of storing the set of reachable vertices within a certain number of hops, right? And this number of hops actually grows exponentially in the number of layers. So it's actually a very efficient algorithm. Um, and we're able to find that after five layers, that the vertex 1 can reach the goal 9. So it seems that transformers can learn a generalizable search algorithm, but we've only tested it, we only observed this to be true for kind of intermediate and smaller size graphs, because they do struggle to actually learn the task for very large graphs, as we saw, right? But this does suggest that even if scaling alone doesn't address kind of this inability to search by language models, new training methods may be able to do so, right? And we have some preliminary results that are unpublished showing that new techniques like curriculum learning might be used to train LLMs to perform depth-first search on arbitrarily large graphs. For example, so the way that curriculum learning works is that you start with a very simple distribution over graphs, maybe like only look at small graphs, and then wait until your training accuracy reaches a certain threshold, like 98%, right? And then you progressively increase the size of the graphs, the complexity of the training samples, right? And then again, wait until the training accuracy reaches a threshold, and then again increase the difficulty of the training set. And then you do this until eventually you cover the full training set. We also have found through separate experiments that reinforcement learning can be used to teach LLMs to search on arbitrarily large graphs, but only if the training data contains examples of large graphs, right? So um, these techniques aren't really solving the problem of OOD generalization, but if you do train the model on large graphs, then it in principle could learn to search over large graphs. Um, and I'm a bit over time, but I want to thank all my collaborators and thank everyone for listening.
Thanks. Very interesting, very thought-provoking talk. Let's see if there are already questions. So yeah, maybe you can you see the question? Maybe you might.
Oh, yeah. Is it in the chat?
There's a Q&A part there.
Oh, I see. Show webinar. Got it.
Can you
More
see it now?
Q&A. I see it now.
So Ben Nguyen had the question.
Yeah. So I don't think we tried. I don't remember exactly how the flood fill method um, is defined, but we did try kind of a different kind of prompting approach called selection inference, um, where basically uh, you allow the model, it's much more flexible than DFS. So every step is broken down into two kind of sub-steps. One is selection, one is inference. In the selection sub-step, what you do is you select a vertex that has an unvisited child vertex, right? And then in the inference step, given that you've selected a vertex, you pick one of the unvisited child vertices to visit, right? And then, as you can imagine, if you repeat this process, you'll eventually search the entire graph. Um, but this, of course, is much more relaxed than DFS because in DFS you have this specific order where you have to you know, uh, backtrack to the most recent parent that has an unvisited child, right? But with selection inference, you don't have this constraint. Um, but as a high-level summary, we didn't really find any qualitative difference in the behavior of the model learning to do selection inference versus DFS. That's why I kind of excluded those results in this talk. Yeah, that's a good question though.
Okay, so Let me ask one question. So it's very interesting. So when you look at the Tower of Hanoi, right? And when you say the models were failing at the depth go, I did not understand. Are they giving wrong answers, or they were getting stuck? So or or whether you differentiate between them?
Yeah,
Actually,
so
one more problem there is also that for that particular problem, you may, I mean, let's say your exponential step, but you may take more steps, but still solve the problem.
yes.
So yeah, I was just curious for that example, how was it?
Yeah, so for Tower of Hanoi, I think what they did was so what these LRMs do is they output their like reasoning and they put it into like think tags. So they have like a think and then a slash think at the end. And at the end, after the thinking, they will output their answer in answer tags. And so this will just contain the final answer. Um, and in Tower of Hanoi, I believe what they were checking for was the sequence of disk moves, right, that you need to do to get from the start state to the goal state. Um, and I think they were looking for like an exact match accuracy. Um, we did something similar in our graph search, or at least in the symbolic setting, where we require the model output the sequence of vertices going from the start vertex to the goal vertex. Um, but it turns out that like these models are pretty good at like answering something. So like if they fail to find something, if you actually inspect the chain of thought, you can see that, they just end up guessing at some. They'll say, I can't find the answer, so I'll just give a guess. Um, and so, yeah, like when sometimes the model will just keep trying and then fail and then guess, and then oftentimes that guess is just wrong. Sometimes it's actually correct, which is actually kind of interesting in its own in its own right.
Yeah, I guess there is a significant motivation for them to give answer.
Exactly.
I do not know will result into a significant lack of interest from users, and they keep the users. So
Exactly. Yeah, they're not trained to like hedge, unfortunately.
yeah, quite interesting. Let me check if there are any more questions. Well, yeah, I think there are no more questions. So thanks a lot again for a very interesting talk, and see you all guys next week.
Yeah. Thank you, everyone. Thank you for inviting me.